So hello, good afternoon, everybody. Now we start our last lecture in 2021. And today we're going to completely focus our attention on contravariant factoriality. On Levitt. However, before I start with proving for you three lemmas, I think, let me mention that in the new year, we'll have to go back to the covariant factoriality of Kohn and Levitt algebras, because some things that we took for granted as obvious are simply not obvious at all. And I'm not sure if you guess what it was that we missed. I mean, I believe that the statements are true. I started checking them and they seem to hold water, but there are non-trivial arguments proving them. So we definitely missed some points. You see, when I was cooking up some fancy restrictions on morphisms to prove my theorems, I completely forgot that I should check whether they are closed under composition, as otherwise you do not have a category. Right? When you say, all right, I don't take all maps, I take only continuous maps. Well, you're home and dry because the composition of continuous maps is always a continuous map. But now when you look at the M condition, and even worse, if you look at this regularity condition, it's not at all obvious that if you compose two morphisms that are regular, you'll get a regular morphism. And if you compose two morphisms that satisfy the M condition is satisfied. But we'll get back to it in 2022, maybe in form of the exercise. Let us discuss it maybe a little bit at the recitation class. For the time being, I want to focus completely entirely on the contravariant factoriality, because this is all that we can do within 90 minutes. And so this means that I will go over this, how's it called, TB, target bijectivity condition one more time, and I will show that indeed this condition is composable. So let's first recall this condition. I need to recall it because I'm going to work on it. So the triangular bijectivity. And it's not triangular, my goodness, target bijectivity condition. I will skip the words, just write the math. So we had a morphism F from E to F, which is an element in the set of morphisms G, the set of morphisms from E to F, of course. And now the condition is that for absolutely every edge in F, okay, when I take the preimage of this edge, then this set is in bijection by the target map in the graph E. So now this lands in edges of E. So now I can apply the target map of the graph E, and I restrict it to this set. So this is mapping to TE of E. So this is in bijection with the set which I obtain by taking the preimage, of course, again under F of TF of X. Okay, and we argued the last time that this is obviously well defined as a map, and that this is a non-trivial condition that we require its bijectivity. And I'm going to discuss examples later on, again in the new year. But one of the, if you want something really very quick, which I'm going to erase right away. So what works for us and what doesn't. So what works for us is, for instance, that we have two edges like this, and we collapse them into one edge like that. So you see, I have two edges in the preimage of this edge, but when I look at the endpoint vertex, then this endpoint vertex also has two vertices in the preimage. Okay, so if I call it X, Y, and if I call it, say, V, W, and I call this E and U, right? When VW gets mapped to U, and XY gets mapped to E, and when this condition is satisfied. But this condition fails if, for instance, I identify V and the W, if I have something like this, right? Then this will not hold, because we will have only one element in the preimage of U, and two elements in the preimage of E with the target map applied. Okay, so if I take the preimage of V, I have X and Y. Apply the target map, I have V and W. All right, and this is one set. On the other hand, what I can do, I can just take the preimage of U, and here I get V and W. So that's fine. The condition is satisfied. But now here, if I take the preimage of E, then I have my X and Y. Oops! Oh, I said something wrong, I think. No, that's wait a second. Okay, let's take. I take the target map. I applied it to the preimage of F of E, and that set is simply one element set U. Oh, okay. So yes, I know how to fix it. Let's say that this is not U, this is V, and W is somewhere else. That's W. And now I again have VW mapped into U, X and Y mapped into E, and then we have a problem. This target bijectivity condition is not satisfied. Yes, because here the TE of a preimage of E under F is just one element set V, right? But when I look at the preimage of U under F, this is a two element set VW. So there is no way we can handle bijection. Okay. Right. So this is the condition, and here I had it exemplified by an example and a counterexample. Okay. So now actually I'm sorry, I'm still hesitant whether I needed this W, because I see here that in fact I'm claiming bijectivity between a subset of a set of edges and the subset of a set of vertices. So here when I need the bijectivity. So I'm sorry, I don't need this W, because one subset has two elements and the other subset has one element, so they cannot be in bijection. So sorry, this W is not needed. Sorry, that was yeah. This is what happens when you. Sometimes this is what happens when you. Anyway, we'll do some examples later on. I just wanted you to have some intuition of what it is that we assume. But now, first and foremost, I want to prove the lemma that this condition is composable. Okay, so first note that we all decided before, but let me state it, that the bijectivity of F implies its target bijectivity. I can draw the following conclusion. So F equal to identity satisfies target bijectivity condition, okay? Because two things we actually have to check to claim that we have a subcategory. First, identity must always be a morphism, all right? If you make a restriction so weird that identity doesn't satisfy, then sorry, but it's not a subcategory. And then here's this composition issue. So now we'll tackle this composition issue, which is a little bit, well, I don't say tricky, but it's not immediate. I have like 4 or 5 lines of calculations to see it. And it all relies on the composition of certain sets. So what it is that we have to prove, okay? We have the 2 morphisms now, going from E to F, and G going from F to G, okay? And I assume about both of them that they satisfy the TB condition. Okay, so for starters, by the very fact that we are in this category POG, we know that the map which we are talking about is well defined. So for starters, if I take any Y, which is an edge in G, very clearly when I compose these 2 maps, F and G, G circle F, I take the preimage under this map. I take an element in this preimage, so some element E in E1. I map it to its endpoint, so TE of E. Well, then I want my domain to be the preimage under G circle F of the end of Y. So TG of Y. Okay. And it immediately makes sense because if you take any element E which is in this preimage, okay, so this means that G composed F of E is equal to Y. So now when we apply TG to this, by the factoriality of G and F, you will get that this is equal to TE of E, okay? So TG of this is equal to TG of Y. And now you first commute TG with G and you get GTF of F, and then you commute TF with F, and then you have G circle F, circle T, E, and then applied to E. So that works. This is really well defined, okay? Let me, oops, oh, I'm sorry, I erased all drawings here. Okay, but I'm not going to rewrite it. I will just continue with the proof. So we have a map which we know is well defined, and I'm sorry, I clicked on the wrong button and everything was done. And I don't know how to restore it. Maybe there is some command, but I don't know how to do it. I'm sorry, no, undo, wait. Sorry, that's easy actually. I just wanted to raise this one. Okay. So now what remember that we assume both for F and G, this vertex compatibility, target bijectivity condition. So for G, it will read in the following way. I really need to write it explicitly because otherwise it's too difficult to combine it in grammar. So I'm just writing the TB condition. Okay, so I take any Y in G1, and I take the preimage of Y under G. Now I take my map to be the, sorry, I should also write what belongs in there. I have some X, some edge X which is in here. So X is of course an edge in F, so I can apply the target map so X. And of course, this is an element which is in the preimage under G. Preimage under G, or the end of Y. So TG of Y. And this is bijective. Y assumption. this implies, so let me draw some conclusion from this. This implies that again, for y in G1, the following is true. If I take the preimage, well, I need to decipher the right-hand side. So I take this preimage of Tg of y under G. But we assume that this map Tf is a bijection. So this is the same as Tf of G inverse of y, right? That's just by the bijectivity. But that's not everything. Now, if you think about the set, well, you can very easily decompose it. So this is equal this disjoint sum. So this is a disjoint union over all x in the preimage under G of y. And here you just have one element set F of x. Okay. Well, this is true because Tf, when restricted to this set, is a bijection. So in particular, it is an injection. So you don't identify anything. Usually, this equality would be just the usual sum, right? The preimage of the set is the union over all its elements of preimages of all its elements. All right. So this is what I wrote here. But now I use this square cup instead of cup. And this means when I'm taking this joint union, this means that all these sets are pairwise distinct. And of course they are because Tf is injective. If it is bijective, that in particular it is injective. And we know that if we restrict it to this G inverse of y, that's by assumption it's bijective. Okay, so I have this stratification. I'm interested in this set G inverse of Tg of y. Okay, so first I turned it into something slightly different, and then I decomposed it into sort of disjoint layers. And this is going to be very helpful because remember, the preimage always respects decomposition into disjoint subsets. That's obvious because the preimage of two different points must be two different points, because a function can have only one value. A map has only one value. So if x is different from y, then preimage of x must be different from the preimage of y. So preimages of disjoint subsets are disjoint subsets. Okay, so now I can conclude from this something important for our calculation. Again, it holds for all edges in G. I can now look at what it is to take the preimage of G circle F of Tg of y. Well, and of course, this is preimage under F of a preimage under G. Of Tgy. 1, 2, 3. Okay, but now we just computed this part G inverse Tg of y. We just wrote it down here, but this is this disjoint sum. Okay, so now I apply F preimage to this disjoint sum. So this will be the disjoint sum of preimages. So the disjoint union of all x's in G inverse of y of F inverse of Tf of x. Okay. So this way, I managed to decompose the codomain of the map I'm interested in. All right, and now I'm going to do the same with the domain. So next. We observe that again for every vertex in G, for every edge in G. When we just applied to Y, so G circle F preimage of Y. Well, as we already wrote, this is F preimage of G preimage of Y, but now I can write it down as disjoint union of X running the preimage of Y of F preimage of X. Okay. And if you want, now this is precisely the domain of our map. We want to prove a bijection between these two disjoint unions. But in order to do it, we just realize that when we restrict ourselves to these components, so look what happens. Here I have this disjoint sum, and the index set is the same. These are all edges which are in the preimage of Y under G. And here we have F inverse of X. And on the other side, well, we have it what we wrote on the previous page. So F inverse of TF of X. And again, this disjoint sum is over the same set. Right? And here is our map, which we want to prove is bijective. Well, this is a map which maps edges to their endpoints in graph. Yeah, because what we have left-hand side is a bunch of edges in the graph E, and what we have on the right-hand side is the set of vertices in graph E as well. And the map which we are talking about is the target map. Okay, and now it's very easy to see is that if we prove that for every X, the map TE from F inverse of X to F inverse of TF of X is bijective, then we are done, because then it's bijective on the whole set. And to this end, we wanted to use now the target bijectivity condition for F. Okay. So let me write it. This is bijective because I can still write. I can still write. I can write it like this. You know, there's target bijectivity condition for F. Of course, I have a quantifier which says, okay, I take all edges in F, but instead of taking all edges in F, I can say the following. I can take all edges in Y, in G, sorry, all edges Y in G, and then I take all edges in the preimage of G. Right, so this quantifier means that I'm really taking all edges in G, right? And now what happens here? It happens that if I look at the set F preimage of X, I take an edge E here, I apply the endpoint of the target map, I will land in the set, which is the preimage under F of TF of X. And this is bijective. Exactly as I told you, when I restrict myself to these layers to which I decompose my both domain and codomain, it is bijective on each layer, between each corresponding pairs of layers. So it is bijective as claimed. Okay. So summarizing, we have proved the following lemma. Restricting morphisms. Sorry, my handwriting degenerates because I cannot put my hand on the screen. Restricting morphisms. POG. The morphisms. Satisfying target bijectivity condition yields a subcategory. As before, we denote this subcategory by TBPOG. Okay, and now we are ready to prove the lemma, which states the contravariant functoriality of concav algebras for this category of morphisms. And because again we analyzed it before, I don't want to write everything using full English sentences. So let me just write down the very mathematical statement. Our construction is as follows. We take an element in the concav algebra of graph F. The typical element will be the class of chi P, where P is some path in the extended graph. And we construct the map denoted by F star C, upper star C, which maps it to something interesting, namely we take the sum of all Qs in the preimage of F bar of P, all the classes of chi Q now taken with respect to the concav algebra of E. This is an element of CK of E. Okay, so this is our construction, and we have to prove that it's well defined, functorial, and unital. These are the claims. So this is well defined, functorial, and unital. Of course, when we restrict ourselves to graphs with finitely many vertices. So basically, that's what I explained to you a week ago, except that I didn't realize back then that it's not so obvious that we have a category TBPOG, right? But that's what we just proved. Okay. And now we can proceed with proving the lemma. The proof is not very complicated. In fact, it boils down to just one simple calculation. Let me start from another page. So from previous lemmas, and I explained to you the lemma that we had for the path algebra. So remember, a lemma like this is true with given by the same formula. It's true for path algebras. So if I remove these equivalence classes and I remove C, then I just have this claim proven for path algebras, including everything that it's, well, then it's obviously well defined, but we prove it's factorial and we prove it's unital, okay? So as far as the basic step goes, we can use this lemma which is proven for path algebras. And then we also should remember that this extended graph construction is covariantly factorial, because now I'm taking the quotient of not the path algebras of graphs, but path algebras of extended graphs. But this we also checked, Nicholas checked it is factorial. Okay. And now we also know that when we do the restrictions we just spoke about, we really have a subcategory. Okay. So combining all these three previous lemmas, we can claim that we have a contravariant. So using previous lemmas, we infer that we have a contravariant functor which, well, uses the category POG, no restrictions yet. Okay, so the lemma about having a category we proof is going to be used in the next step. I assign to the graph algebra extended graph. To a morphism which for clarity it might be convenient to write down as a pair, you know. And 0, f1. Remember that this is graph homomorphism, so it's given by a map on between vertices and a map between edges. And to this we assign a map from KF bar to a E bar, which is an algebra homomorphism and which we denote just by F bar star. And of course, which is a morphism between algebras of the game. And the formula is what is important. The formula is given in the same way. So if I take any path in the extended graph, IT, any path in the extended graph, I go back to the sum of all things in the fringe under bar P and I Q. And that's an element. So this is obviously well defined because chi p gives me a basis, all right, in KF bar. And but now we also know factoriality and we know unitarity. So now our first step is to make sure that this map is well defined when we descend to compact algebras. Okay. And to do it, so to prove that C is well defined. Remember, we define it as as a quotient map for F bar C, for F bar star, sorry. Let me write F bar star descends to quotient algebras. Well, we have to show that this F bar star preserves the conscriptor relation. Okay. I take any morphism in my category TVPOD. So now I do assume that I have this target bijectivity satisfied, and I have a lemma which shows that this is a category, so my writing makes sense. And I take any two edges in F1. And what is my first conscriptor relation? Well, I have to prove that if I take the class of F bar star of chi star times the class F bar star of chi y, so this is equal to the Kroneker's delta between x and y times the class of F bar star applied to chi tf of x. Okay, so this is exactly the condition for F bar star to descend to the compound algebras. You have to prove that F bar star maps one ideal by which we quotient to the other ideal by which we quotient, which is exactly this equality. And of course, it must hold for any morphisms because we're doing it in full generality, and it must hold for any edges xy in F. Okay, so that's what we want to compute. But first, note that this is equivalent to something slightly nicer. I have to change the page. Okay, so first we have the same quantifiers. Let me not write it down. Quantifiers are changed. But now I can write it down in the following way. I can write it down as just the sum over EX running inverse of X and EY running also, no, and EY running the pre-image of Y, okay? And here we have the class of I EX star times the class of I Y. On the left-hand side, just the Kroneker's delta XY. And then the right-hand side, well, the right-hand side is also slightly changed because I'm just applying this map. I'm telling you what it is. This is the sum over all these in the preimage of TFF, preimage under F bar of TF of X. Sorry, I said F, TF of X. Okay. Kroneker's delta, so I choose X or Y is relevant. And now, of course, we have a class of chi. So what I did on the right-hand side, I simply applied the definition of my morphism F bar star to vertices. And now, in fact, I can erase this bar because this is a graph homomorphism So vertices in the image of vertices only. That's not the case in other categories where we have path homomorphism of graphs. Then we can shrink a loop to a vertex, as you saw in an example. But here's not the case, so we can just and anyway, even then the bar would be relevant because bar is only about stars. So here it's just clear. I can simply write F inverse, or I could even write F0 inverse if you want. I can also write F0 inverse. Okay. Right. And what did I do on the left-hand side? Well, let's see. I also just applied the definition, right? So I'm taking the preimage, but here you have to bear in mind the following thing. I'm taking, say, the preimage of y under f bar. So what is f bar preimage of y? Well, remember how the barred maps are defined. They map starred edges to starred edges and non-starred edges to non-starred edges. These are like two disjoint subsets that are never mixed, and they're not mixed by the induced morphism. Okay, so if I take the preimage under f bar, it's the same as taking the preimage under f. Okay, because there is nothing in the star sector in the opposite graph part that is going to be mapped by f bar to y, right? That's how we defined f bar. And very much in the same way, if I look here, say instead of y, I look at x star, well, then x star can be the image only of something which is starred, okay? And we can conclude. Let me now erase the right-hand side. That this must be equal to the preimage under f of x and then star. Okay, because what do we know? We know that this is equal to some, I don't know, y star, right? And we say that this holds true. I mean, this is the equality of sets. Okay, this is the equality of sets. So let me maybe write it down in a different way. Well, take an arbitrary element in here, call it y star, and then y star is an element here if and only if f of y is equal to x. Oops. Oh, I jumped into the next page. I know how it happened. Okay. If and only if fy is equal to x. Okay. And when you look at this side, well, y is an element here if and only if f bar of y is equal to x star. Okay. But this means that f of y has to be equal to x. Sorry, here I forgot to write the star. Yes, I write y star. Yes, again we know that in the preimage of starred edges I can have only starred edges, so I can, without loss of generality, write y star. And when I write what it means that f bar y star is equal to x star, we know that f bar of y star is f of y and then star. And when I have f of y star equal x star, it means f of y equals to x. Okay. So that these are some trivialities, but these are the trivialities I'm not writing in my lecture notes, but I'm using in my calculations. So now if I want really to compute, I need some light because it's getting dark. We're about to get the shortest day of the year. I mean, in this case, yeah, the longest. Okay. So now I hope it's crystal clear. I will raise it. This was just a side remark of things that you should do in your memory. Yeah, that's what explains this calculation, right? So instead of taking the preimage under f bar of y, I take preimage under f. And instead of taking the preimage under f bar of x star, I take the preimage of x under f. And then I start at the right place. Okay, so this is exactly the formula. I just applied the definition of f bar star, nothing more. And that's what we have to prove. So first, let's prove it for x different from y. And I claim that this is obvious. Why? Well, the right-hand side is obviously 0 by definition, but then the left-hand side, why is it 0? Well, this is 0 because, let me write because. Then the preimage of x and preimage of y do not intersect. So this means that ex is never equal to ey, which by the constant relation means that we have a 0. Okay, so these two sets, f inverse of x and f inverse of y, are disjoint. So this means that ex and ey are always pairwise different. So this means that we always sum zeros on the left hand side. Okay, so now we can take x equal to y. So for x equal to y, using, of course, target bijectivity condition, we compute. I have a sum. So now I can just, I have E1, E2, but running the same set, which is pre-inverse of x. I have I E1 star times chi. Right. And well, by the first cosquare relation, I know that E1 has to be equal to E2, otherwise we're getting 0. So all these off-diagonal terms will be 0. So this is nothing but the sum over just one variable, E running f inverse of x. And now we have the class of chi ex, of chi e star times the class of chi e. And by the Kunz Krieger relation, we know that this will just give us endpoints, right? So this will be the sum. And here we will use, so this looks very innocuous. The last step looks very innocuous, but this is in fact where we use the power of this target bijectivity condition. So here I'll still write E as my variable. But here this simplifies. This is chi of t, E of E. Right, by the constant relation. But we are not home and dry yet, because the sum that we have on the right hand side is over a different set. So we better have these sets in bijection, otherwise we'll get different sums. And it doesn't help if all elements of the sum are the same, because if I add the same element to itself a million times, it will not be equal to itself, unless we're in some stupid characteristic field. Okay, so here I use the TB condition. I relabel the sum over the bijective set. So I relabel over vertices V, which run the preimage of TF of X. And now here I of course write right? You can clearly see that, well, what is V? V is, wait a second, yes. Yes, yes. This is my map. You see, this I have this map TE, which goes from F inverse of X. I go by TE to F inverse of TF of X. Okay. So you see what I'm putting as a label are elements of my codomain. So I'm having the sum over all these running the codomain. And because I have a bijection, well, this means that the sum are equal. And I think this does the job, because if you look at the right-hand side, this is exactly what we have, the sum over V running the preimage of TF of X, all right? So we proved that the most interesting part, that F star C is well defined. So summarizing, F star C is well defined, and of course an algebra homomorphic by construction. Okay, so let me write down is a well defined algebra homomorph. And I want you somehow to recognize that this last step is subtle, and exactly when you do it on the example I told you, where I have two edges meeting in one vertex here and one edge there, right? Then there is a trouble, because here we have this vertex V twice, because I have two edges, right? I have my edge E1, I have my edge E2. So when I look into the sum on the left-hand side, I have chi V once and I have chi V the second time. So I have 2 times chi V. Whereas here, the preimage of this vertex is only V. So this sum has only one element. And this is not true that, in general, it's not true that 2 plus chi V is equal 1 plus chi V. Of course, it can be characteristic 2 and so on. So it might hold, but in general, this is not true. Okay, that's why, I mean, we really needed this condition, but it's very easy to overlook, because you might say, well, these sums are the same. Well, they're not the same unless we have this bijectivity condition. Have you got any questions here? Okay, so now let's wind it up, because the rest is really easy. So the factoriality again is immediate. F circ G C. This is equal to AC star circle F C. Well, it follows immediately the factoriality of F bar star. Let me write it like this. If I have F circ G bar star, and this is G bar star circ, and this, you know, this was proven before, right? And because here we do nothing but go to the quotient, which is now well-defined procedure, we proved it. we have functoriality by the functoriality, which we claimed at the very beginning of the proof. So finally, the unitality. C. Of course, for graphs with finitely many vertices, follows from the following simple observation. If I take the pre-image under F bar of all vertices in F bar, well, first I realize that all vertices in F bar are all vertices in F, and then this is a graph homomorphism, so only vertices are mapped to vertices, so this is the pre-image simply under F. Okay, but again, by the sheer fact that you have vertices always mapped into vertices, you know that this pre-image is the whole is zero. Okay, and then this is the same as E bar zero. So if you know these trivialities, you can just compute that F star C of 1. Remember, 1 will be the sum over all vertices of F. Sum over all V in F0 of F of star ID. So I just wrote 1 in CKF in the conpath algebra of F, and I applied this F star C. Okay, so now I'll have a sum, and now this will be a sum over all vertices W, which are in the pre-image under F of F0. And here I have just chi W, the classes of my W. Okay, that's just applying the definition of F bar star. Okay. For every V in F0, I take a sum over a pre-image of V. But remember that what is the pre-image of a set is the union of pre-images of all of its points. So I can just write it down as one neat sum. And now I have to use the thing which I got for you before, right? That this is really the whole is zero. Right, that's this part here. So W simply runs all elements in E0. But then obviously this is 1 in the conpath algebra of the graph E. So I guess this proves this lemma. And yep, we have half an hour to prove a second lemma and be over and done with the contravariant functoriality of Kohn and Levitt path algebras. So now we want to upgrade this lemma from Kohn path algebras to Levitt path algebras. And I say upgrade because by this EX construction, we proved that Kohn path algebra is always a Levitt path algebra, but for some modified graph. Okay, so in a way, Kohn path algebras are special cases of Levitt path algebra. So that's why I call it an upgrade. And indeed it's an upgrade because now we have to not only make sure that the first configuration relation is satisfied, but also the second one, which is usually more tricky. And here I must say that when I proved it today in the morning, I got a nice surprise because we have to make an extremely mild and trivial restriction on the morphisms, very, very easy to be fulfilled. And then the same condition, TB, target bijectivity condition, makes it work also for the second Kunstkrieger relation. I must say that I was quite amazed because in the covariant factoriality case, the M condition and the regularity condition were completely different. Both of them were serious, non-trivial, and highly restricting conditions, right? Well, here this target biodistributive condition, of course, is also highly restricting, but it works for both constrictor relations. So this is quite awesome. All right. So what it is that we need to assume? Well, we need to assume what I can call complement regularity or contravariant regularity. Let me write it down. How to upgrade. Let it. Algebras. We need one more restriction. Well, namely, I need to know that f of the complement of regular vertices in E is mapped to the complement of regular vertices in F. So if you want, this preserves the irregularity. Instead of preserving regular vertices, it preserves irregular vertices. And of course, you know that this is a different condition than saying that we map regular to regular. Just have a look at the following simple picture. So this is my regular subset here. This is my regular subset there. Okay. And it is one thing to say that everything from here will be mapped inside the subset, but it does not preclude you from having something outside of the subset being mapped into the subset. Okay. This does not violate the condition that regular vertices are mapped into regular vertices. But now we need a different condition. We need to know that irregular vertices, vertices that are not regular, are mapped to vertices that are not regular. Okay. So for instance, what we preclude is the situation in which we have this as our graph E. This is our graph F. So say U, V, U, V, W. Say this is E, and this is prime. So this F is just putting the left graph as a subgraph on the right-hand side. And you see that it doesn't work because the sink V on the left-hand side is mapped into a regular vertex V on the right-hand side. So this is a no-no. We do not allow it. Okay. And in fact, you can nicely see that the level of graph algebras, if you take the Levitt path algebra of this graph here, you would have 3x3 matrices. Whereas the Levitt path algebra of the left-hand side means 2x2 matrices. So we need to have a map from 3x3 matrices to 2x2 matrices. But by dimensional count, it would have to have a non-trivial kernel. And the non-trivial kernel would have to be an ideal in my algebra, which is impossible because M3K is simple. It has no non-trivial ideals. So you know, that condition is actually quite important. And as simple as it is and innocuous as it looks, well, we really need it. We really need to have it. So now let me erase this picture. Yeah, I have one spurious parenthesis. But now note that this is equivalent to the following. When I take the preimage of regular vertices in F, it is contained in regular vertices in E. Okay, that's equivalent. Well, do we see it? Okay, so assume the first condition holds. Then I can take what's this simply? I know it's trivial, but sometimes it's most difficult to say trivial things. Okay, I want to assume that the top condition holds, and I want to prove the bottom condition. So what I know is that if x, a vertex v is not regular in E, that it implies that vertex v is not regular in F. So that's the first inclusion. And what's this inclusion? V is an element here. When F of V, okay, so V belongs to of F. If F of V is regular. Yes. Okay, I need some more space. I guess it's going to be easier with this picture. So the subsets are the subsets of irregular vertices. Okay, so actually in the picture it's so easy to explain. When I have irregular vertices mapped to regular vertices, when I take an irregular vertex and I take the preimage, of course, no irregular vertex can be in the preimage, as it contradicts the condition that irregular vertices are not mapped into regular vertices. So this way, I see this top to bottom implication right away. Sorry, I just said it in words, but I don't want to waste time writing it. And how about the other way around? And to prove the other way around, let's you see, if you want to prove that P is if and only when Q, then you do two things. You prove that P implies Q, and you prove that not true that P implies not true that Q. Yeah, that's the same thing. When you are done, but it's just easier to do implications from left to right. So that's why let me use this logic here. So I just proved that P implies Q. Now, what does mean not true that P? Not true that P means that there exists an element on the left-hand side which is not element on the right-hand side. Okay. So this means that there exists some vertex V that is not regular, but F of it is regular. So V is in here. So not in regular E. Okay, when I take F of it, and I am to be beyond this set. And to be beyond the set, I have to be actually I have to be regular in F. Okay. Am I sure that I do it correctly? I want to negate this inclusion. So there exists X in this set, which is not in this set. here, but not in this set means being regular. So X must be regular. And my X is f of V. Aha, but V is not regular. Okay, this is the mistake I made. Okay, so there exists a vertex which is not regular, whose image is regular, right? But then the same vertex falsifies the other inclusion. Because I take this vertex here. So if you want, this means that V is in the preimage under F of regular vertices in F, right? But it is not regular in E. So this means that F inverse regular F is not a subset of regular E, which falsifies the second inclusion. Okay, these were some trivialities in set theory. But this is a lecture course, so we should look at all details. I hope you don't mind. All right, so that's the form in which we're going to have it. In fact, I could have skipped the first condition and just write about preimages. But I don't know, somehow I thought that this first form is more elegant. Anyway, that's what we assume. And now it is clear. So this time it is clear. No proof needed. That restricting morphisms in what is it, TBPOG to the morphisms satisfying, we call it CR condition. I don't know, a contravariant regularity, you want to call it, or complemented regularity, I don't know. But I had to distinguish it from regularity itself. So I call it CR, okay? So this time it's clear that the restricting morphisms in TBPOG, what the demonstrate is, to the morphism satisfying CR yields a subcategory of TBPOG. And you'll not be surprised that we denote this subcategory by CRTBPOG. It looks like they're doing some genetics. It looks like a genetic code. Have so many amino acids combined. Yeah, I know that it's a bit ridiculous to have a category defined by how many, 7 letters, but I don't have a better idea of how to do it. It's probably still better than using lots and lots of fancy words. Okay. Okay, but why is it clear? Well, obviously the identity satisfies this condition, right? If F is identity, then we have that the regular E is a subset in regular E. That's obvious, and the composition is also obvious because if you compose 2 morphisms and both of them satisfy CR condition, then the composition, so does the composition. That's completely clear. I'm not going to write it down. So now we are ready to formulate and to prove the lemma of today. Which is the upgrade of the previous lemma now to the realm of Levy-Pavlov. the assignment. Wow, and now to really fit it in some space. C R T B P O G. And at the level of objects, of course, nothing happens. We just assign a Levitt path algebra to graph. So it's more convenient for me when I put my hand on the screen, but when I make the spurious marks. So that's the disadvantage of teaching from home. I don't have such a super duper professional writing tablet, just my laptop computer screen. Oh no. Okay. Let me skip writing this monster. What we have here. And again, if you are pedantic, you see here, because we take notoriously pre-images, being pedantic of what we mean by F is important, right? Because back then we simply were talking about the map from finite paths to finite paths. As length was not preserved, that's it, okay? And we could even have edges mapped into vertices, so everything was mixed up. But here, because it's a graph homomorphism of algebras, in fact, we're just getting two maps, and two maps only, from vertices to vertices and from edges to edges. And out of these two maps, we compose the induced map between paths. And this is what I mean by this letter F, but in fact, it's a pair F0, F1. And when we talk about pre-images, I think it helps to say that we have F0 or F1, because then it's crystal clear what is the domain. You see, the concept of a pre-image does not make sense unless you specify of what you mean by the domain of your map. So quite often you have one and the same formula for a map, but you change its domain. You take some restrictions of your domains, and then you write the same symbol because the map is given by the same formula. But when you look at the codomain of such a map, well, you better make clear of which restriction of the map F you are talking about, because otherwise you'll get completely different sets. Okay. So I can here be a little bit pedantic, and when I write a morphism from E to F, I write it as a pair F0, F1. And what we've got an algebra homomorphism from the Levitt path algebra of F, remember it's a contravariant functor, to the Levitt path algebra of E, which we denote as F star L, and of course it's a morphism of algebras of the K. And the formula is, of course, the same, right? I take a class in LKF, a class of chi P, because everything in LKF is a linear span of chi P's. And I map it to the sum over all paths in E bar, which is the F bar pre-image of P. Now, mind you, I'm not telling you that P is only start or non-start. This might be a two-color path having both start and non-start edges. All right, so I really cannot reduce it right now to F. That's just F bar of P, because P is a path in F bar. Okay, and now I write, of course, the class of chi Q. So that sum is an element in the Levitt path algebra of E. Okay, so the claim is, so that's the definition of the assignment, and the claim is defines a contravariant functor And furthermore, also in Italic. So furthermore, the same assignment. Restricted to the subcategory given graphs defined by the vertices. Use a contravariant functor to the category of unit of algebras. Okay, so that's the lemma of the day. Well, we have only 8 minutes, but I want to prove it. Maybe we will extend it a little bit and then shorten the recitation class, but I really don't want to postpone the proof for the next year. That would be a mistake. Okay, so let's prove it. So as we did it in the covariant case, we base it on the conpath algebra lemma. So following the preceding lemma, it suffices to show that this F star C descends to F star L. Let me write it down as an explicit condition. So for any regular vertex W in F, take the sum over all edges which are in the frame, which would begin at W. And now I take the sum over two variables, but running the same set E1 and E2, running the preimage of X. And here I write chi E1, the class of chi E1 times the class of chi E2 star. And this has to be equal to the sum over all vertices V, which are mapped by F0. So I write it as F0 inverse. And here we have classes of V. Okay, so that's what we have to prove for any regular vertex W in F. And I hope it's clear that the rest follows, because if you look into these two lemmas, what they differ by, the only thing that they differ by is that I changed L into C. Everything else is exactly the same, okay? So because we proved it in the case of conpath algebra, and the late path algebra is just a quotient of the conpath algebra, then things like functoriality, unitality, they trivially hold the moment we prove that this functor descends to the Leavitt functor. In other words, for every morphism F, which satisfies yes. Yes, so it's important that we have one more condition, right? And that we use only to make sure that this map is well defined on the course, right? So one more time, the moment we prove that the assignment which we proved was a contravariant functor descends to the quotient construction, things like factoriality and unitality we have automatic because it's just a trivial calculation on equivalence classes. Okay, it holds immediately, just as it was in the covariant case. So the name of the game is only to prove that the thus defined map is well defined. Then it's also automatically, of course, an algebra homomorphism. So it is a morphism where it should be. And of course, on one hand side, we define Leavitt-Pav algebras as quotients of Pav algebras of extended graphs, but there is this intermediate quotient of con-Pav algebras. So we can also view them as quotients of con-Pav algebras, and that's how we view them here in this proof. Okay. So I hope I made my case that all that I have to prove is just this one condition. So now let's do it. I hope we will do it within 18 minutes as well. Okay, these are just two calculations. So for starters, note that CR condition, the new condition, right? Applies the following calculation. Or maybe let me write it like this, allows us to compute. To compute the right hand side. Okay, because what is the right hand side? Well, this is a sum over all vertices that are mapped by F0 to W. And I take chi V, the class of chi V. But now I split this set. Okay, I split it no, sorry. Now I'm using the fact that this is where the CR comes into the game. I know that the preimage of a regular is regular. That's what I'm using it right now. So I can rewrite class of chi V using the second Kuhn-Square relation in the Leavitt-Pav algebra of E. So this will give me the second sum. So the first sum is unchanged. These are all vertices that are mapped by F0 to W. Now I have a second sum. This is the sum over all edges emitted at V. And then I have the class of chi E times the class of chi E star. Right? So here CR comes into play. Because if we had an irregular vertex, well, then we couldn't change chi V to this sum. It works only for regular vertices. If it were a sink, the sum would be empty. It wouldn't appear here. If it were an infinite emitter, well, there would be no finite sum that would fit here to give us chi V back. All right, but now we can, you see, we can continue computing by manipulating the set that we have here, you see. So I'm taking the preimage of the preimage. So this is a sum over all E, which is in the preimage of F naught composed with SE minus 1 W. Right, so I'm taking all W's which are in the preimage of all these which are in the preimage of W, and then all E's in the preimage of these V's. So in fact, I'm taking E's in the preimage under SE of the preimage under F naught of W. but this is the same as the preimage under F naught circle SE. Yeah, because F naught circle SE preimage is SE preimage of F naught preimage, which is what we have here, right? So here we have the same sum. This doesn't change. Well, but now let me save space and not rewrite it. Remember the factoriality, the definition of graph homomorphism means that F0 circle SE is the same as SF circle F1. So let me just erase it and write as SF circle F1. F1. Okay, that's by the definition of a graph homomorphism. Okay, we haven't changed the map, so we haven't changed the set. But now we can split it again into the double sum, and it will look like something that we want. With a sum, because you know, preimage of the composed map, so it will be F1 preimage of SF preimage. Okay. So first I'll take this SF preimage. So I take all x's that are running the preimage F of W. And then I take all e's that are running the preimage of the F1 of x. And of course, what I multiply is not changed. The class of chi e times the class of chi E star. Okay, this should be SF. Yeah, that happens in F, right? Because I put x into the right hand side, and I have F1 preimage of SF preimage, which is exactly what is up above. Okay, and this is where we stop our calculation. We cannot go any further from the right hand side to the left hand side. But now to complete the proof, we just make one step on the right hand side. And here came my big surprise, because you see here we used our new condition. So everything is cool as you expected. You have a new condition, and this new condition allows you to prove a stronger theorem. But to my great surprise, the calculation of the left hand side just uses again target bijectivity condition. So now, using the target bijectivity condition, we compute the left-hand side. And what is the left-hand side? Well, it looks almost like what we've got, what we need, but it has sort of too many variables. So again, my first sum is over edges that are emitted as W. And then my second sum is over two variables, E1 and E2, which are in the preimage under F1. Okay. And here we have I E1, the class of I1 times the class of I E2 star. Well, and here I have a certain problem because we have cross terms. Remember that this is the second Kunstkrieger relation, that we have chi E1 star chi E2. That's equal to Kroneker's delta of E1, E2, blah, blah, blah. Okay, but not in the other way around. If I exchange the order, this is not necessarily true. Okay, so what makes it multiply to 0? Well, just the path algebraic relations. You see, if E1 and E2 end at the same place, that's my E1. So this is my E1, this is my E2. If they end at the same vertex, then E2 star begins where E1 ends. So E1 E star is not 0. But of course, if it so happens that the end of E1 is not the end of E2, that's it. Then this is zeroed by path algebraic relations. Okay, and we have it here. We have it here exactly by target bijectivity, because look, we are looking at this set f prime of x, and we are looking at the map TE. We're looking at the map TE, and we are saying that this map, when restricted to this set, is bijective. So in particular, it is injective. So whenever my E1 is different from E2, the endpoints are also different. So this means that these guys multiply to 0. Okay. So for me, it was a beautiful surprise when I was computing it in the morning to get this proof. So 4th time in a row, we are learning something new, just discovered hours ago. So let me, okay, erase also this one. Yeah. So this is equal YTB. Just diagonal sum. So here it's just sum over x, emitted at W. Here I have sum over a single variable E, which is in the perimeter under F1 of x. Now, of course, I have chi E star. And lo and behold, this is the right-hand side. So this is equal to the right-hand side and ends the proof. Okay, can double check. You see, this was my left-hand side. Sorry, this was my right-hand side. And this is identical to what we just obtained from the left-hand side. So we are done. We proved that this is well defined, and the rest we already discussed. So we proved our case. Let me, maybe because I don't want to end that awkward hour, let me continue for these 7 more minutes to tell you of what we still want to do. This is about now covariant functoriality of Kohn and Levitt path algebras. But maybe first, have you got any questions concerning these two lemmas? No, I don't hear any questions. So in this case, no, actually, no, it's better that instead of going into the covariant situation, we maybe look at examples and counterexamples for the contravariant situation. And yeah, we already did it in a way, but let's, I mean, we did it very briefly, so let's do a little bit more. So for the CR condition, right? We had this example. So U, V, W, X, Y. This is mapped by F to. Sorry, this is the other way around. Okay, so let's change. And UV. So this violates CR. Okay, because irregular vertex V is mapped into a regular vertex V. But now we can do it we can do it also in a different way. How about now having F, having such a thing, having an infinite emitter, so VW, I have an infinite emitter. And now say I map it to just a regular vertex like this. Okay, And is it a graph homomorphism? Yes, because I map vertices to vertices, I map edges to edges, and I preserve the start point and the end point. So that's a legit graph homomorphism. But it also violates the CR condition, because my vertex was irregular in E and is regular in F. Okay. And well, what does it tell you at the level of algebras? You have something very funny, because it tells you that if you have arbitrary size finite matrices, that's a non-unital algebra. Oh, sorry, no. This is one completely. I'm telling you something wrong. Yeah, this is okay. So for graph sister algebras, let's do it for graph sister algebras. For graph sister algebras, this will be the minimal initialization of compact operators, which is also known as the sister algebra of a standard Podlesh quantum sphere. And we would like to have a map, because now it's contravariant functor, from 2 by 2 matrices. And apparently such a map I don't see why such a map should not exist. Okay, so let's see, because here that's kind of crystal clear to me. I should not expect having a map from 3 by 3 matrices to 2 by 2 matrices. Maps hardly ever exist. But what's wrong in here? Okay, so let's see why what would go wrong in our reasoning where we needed this CR. Well, we needed it for the first Kohn-Krieger relation. No, sorry, this is yeah, we map something irregular. So here that's a bit tricky because I don't have anything ending in V. So that's why it might work. Okay. Because V is a source. You see, I have a feeling that this map should exist because after what are compact operators? This is a sister completion of arbitrary size matrices. And of course, 2 by 2 matrices should fit inside. And I think here we wouldn't violate the condition because we don't have any edges ending at V. Okay, so we would not get any contradiction this way. So it just occurred to me that we can actually weaken a little bit this CR condition. You can exclude sources. Yeah, it just occurred to me that maybe a more general theorem can be proved if we modify. You see, this is why it's so important to do even stupid examples. Yeah, I'm pretty certain that if I would replace this E0 by this E0 with sources removed, so instead of E0 and F0, we would have all edges that are not sources. So they must receive at least one edge, because only then we can compute the Kohn-Krieger relation. That's all we need here. We don't need to discriminate sources. Sources can violate this inequality. There's nothing wrong if I have an irregular source mapped into a regular source, because still it's a source, so there's no Kohn-Krieger relation over there. Okay, so that's the way we can modify it, And because I see, again, I see nothing wrong with this example here, but if I would put here one more edge, well, then this would really violate it. This wouldn't work. Why? Because V is still irregular. Okay, and now it is mapped into something that is regular. It emits just one edge, but it receives is maybe irrelevant, but it definitely emits one edge. And here we would have a problem, because if we look at, say, let's call this X, and I'm trying to compute F star of X. Okay, and now this well, normal would be the sum under the preimages of X, but here there's just one edge in the preimage, so there is no sum. Maybe I should somehow distinguish them, because otherwise it's too confusing. So this I will call Y. Okay, so by construction, because there's only one edge X which is mapped to the edge Y. All right, the preimage of X is just equal to Y. Right, I think this is correct. Yes, and now I want to verify the first configure relation. So what I'm doing is the following. I am checking X star X. So this will be mapped to Y star Y, which is V. But X star X is V on that side. No, I don't understand. So what? Nothing goes wrong here. Where did I need this CR condition? Yes, okay. Oh, yes, of course. That's for the second. Yes, that's for the left. I'm sorry. This is, of course, for the second configuration relation. So, of course, I cannot violate it with the first configuration relation. Yes, I'm sorry. This is what happens when you don't sleep much enough. Okay. So we were looking. All right. So I take it back. Maybe here we'll see what goes wrong. Let me remove extra edges, and maybe we'll see what's wrong. So here we have, let's call it X again. Oh, no, it's too thick. So we have XX star is equal to V. All right. And now when I look, yeah, and yes, here's another problem. I mean, this map is not proper. Okay, this map is not proper. So the way I want to define it, it just doesn't make sense, because the preimage of this one edge is these infinitely many edges. So that's not proper. So this goes wrong already here. So the map is not well defined simply. Okay, but which surprises me, because but of course, maybe the map, which seems to be given by some natural kind of an inclusion, but this inclusion probably would not be unital. So maybe this is what goes wrong. But definitely this map is not induced from here, because this is not well defined even at the level of path algebras. Okay, so I apologize. This improvisation led probably into more trouble than advantage, but so I retract my statement about sources. This is a confusion of Gunst-Krieger relations. I give you here these two examples where CR relation was violated. One because of having a sink, and another one because of having an infinite emitter. But I'm kind of irritated that this is not the proper map. I'm wondering if we could somehow remedy it by saying, there's no way to remedy it in this picture. This would not be a proper map. So this is simply not proper. Okay, so it violates CR, but it violates CR not in POG but in OG. Okay, and this is the time to end. And let's resume a 4:15, so in 22 minutes. Okay, I stop recording. Thank you very much.